Okay, so the outline will be like this. I'll first mention what this half quantum vortex is all about and what makes it interesting, and then I'll discuss like how you can have this half quantum vortex. But first, let's talk about what half quantum vortex is. So, basic fact that everyone knows is that there's flux h over 2e flux quantization for vortices in superconductor. And one thing we need to recognize here is that this flux quantization is intimately connected with the fact that around the vortex you need to have 2 pi phase winding in order for the condensate wave function to remain single value. So it's very surprising actually to, in this sense, to talk about h over 4e vortex, because this is clearly indicating that as far as the overall phase is concerned, you only have pi phase winding. So the question is, how can you really have this pi phase winding and your condensate wave function remains single value? Well, that is possible only because the systems that will support these half quantum vortices would have 2 components. So therefore, you can have a situation when you have pi phase winding in the pi winding in the overall phase and pi winding in the relative phase. So in other words, what this means is that if you happen to have a condensate which can support this kind of half quantum vortex, that can be an indicator that your condensate has 2 or more components. And then the question is, what kind of system can support these kind of systems? One case that was discussed already back in the mid-80s is this spin triplet superfluid and superconductor with like helium-3A and the A phase of helium-3 superfluid, and more recently strontium-luteinate. And these has attracted a lot of attention in recent years because of the possibility of the vortices, these half quantum vortices having non-abelian statistics.
Another example is a polar phase of spin-on BC.
Let me see the pole.
Polar phase is solid.
Yes, I think that should also work. Yeah. Basically, 2-component condensate always.
But actually, split component, but the same thing.
Yes. So now the second order of business is, so what is it about the spin triplet superconductor that makes half quantum vortex possible? Now, spin triplet superconductor is quite different from this spin singlet superconductor. In spin singlet, the pair wave function is just, the pairing gap is just a scalar, so it has just the magnitude and phase and that's it. However, if you want to talk about the spin triplet pairing gap, then you actually need to write it down as in terms of tensor. And so, because you have more than one possibility of this pairing state as far as the spin degree of freedom is concerned. And this in turn can be parameterized by this D vector, which is defined this way. And in the case that your condensate is not spin polarized, this D vector is going to be real. And for our purpose, let's concentrate on the case where this D vector is uniform in case space, either uniform in case space or confined to a plane. And I'll be mainly talking about the case where it's just uniform in case space.
So you're looking at non-spin polarized?
Yes, I'm talking about non-spin polarized case. So in that case, what happens is, we can always choose our spin quantization axis in such a way that, or D vector direction, D vector axis in such a way that one of the D vector component would be just 0. then what we're going to have is that is like effectively taking some equal spin pairing axis for the spin degree of freedom. And what that immediately tells us is that for this case, we have this. We have two. We certainly have two component condensate, and this direction of the D vector in plane would actually give us the relative phase between these two components of the condensate. And also, the fact that our two components of our condensate is defined as up-up Cooper pairs and down-down Cooper pairs also gives us physical interpretation of the relative phase between these two condensate. So what we have is that if the relative phase between these two condensate is defined as alpha, the gradient alpha would be proportional to the spin supercurrent. And now we can see how we can have half quantum vortex in P plus IP superconductor. What would happen is that if we around half quantum vortex, we have pi winding the overall phase, and we would also have the reversal of the D vector direction. That would keep the order parameter single valued everywhere. And in addition, what we would have is the spin supercurrent circulation around this half quantum vortex. And also, we find something else. Since we have this pi winding here, and also pi winding of the alpha, that is to say, B vector going from, say, plus x to minus x here, what we actually have is, if we have half quantum vortex, the situation we can have is that the down-down Cooper pair, for instance, would have 2 pi phase winding, while the up-up Cooper pair would have no phase winding at all. Or we can have vice versa. The implication we have here is that whereas we have, for normal, conventional H over 2E vortex, we have normal, the core of the vortex should be normal, but here actually, core of this type of half quantum vortex would be actually still in the superfluid phase. But it will be in different, in a sense, it will be in different phase from the rest of the condensate. So if the rest of the condensate is in A phase, at the core, only like the down-down pairs remain while up-up pairs are already paired. So we have like an A1 phase at the core.
But so here D vector is K dependence, and the entire K dependence is just Kx plus IKY, right? Everything is multiplied by Kx plus IKY.
Yes, but that actually is not a must condition actually. If, for instance, one case we can think about is what's called B1 or planar phase in helium-3. There it's like the up-up pairs have P plus IP pairing and down-down pairs have P minus IP pairing. But it can be still described in this equal spin pairing language. So everything would actually work out almost the same way. D vector would look a little bit different, but because it is K dependent after all there. But how you can describe it is that the angle between K hat and D hat would actually wind around the vortex by pi. That would give us almost exactly the same physics.
And so you will still get all this physics and the vortex and the states inside the vortex, right?
Yes, and difference really arises only because of the case where we couldn't spin over coupling.
Okay, but it would be a different symmetry class, wouldn't that be? If understood as topological insulator, that would be a different topological insulator.
Yes. Yes. It doesn't break time very specific.
So what phase is this?
Well, this, if you want to just take this as, let me see.
Is this like a B phase or which phase? I forgot. Just so we have
Actually, this would apply both to, let me see.
A phase.
This would apply primarily to A phase, but it can be applied to this planar phase with very little modification.
Well, I don't understand Victor's comment about D vector being K independent. I mean, doesn't it have at least Kx plus IKY dependence? So
constant. The y is
Oh, yeah, but
so
it's,
we'll have to take that out.
yeah. Well, I think yeah, you're right. The correct language I should have used is that the k dependence of d vector is uniform. That's not changing as we go around the vortex, really. Except in the terms of like overall phase.
Meaning D points.
Well, d of k is a constant vector times kx plus iky.
Yeah.
Okay, that's fine. Okay.
Well, I'm not quite sure whether this argument can apply to B phase. I think this argument should apply to A phase only.
Oh, I'm talking about the B phase where dz is 0 and we are completely ignoring spin over coupling.
Yeah.
One of the components is totally turned off, and
So
it's certainly not going to apply to the isotropic B phase. I agree 100% with you.
yeah. Because you need to assume equals compare.
Yeah, but like if you have a planar B phase, I think it's called B1 phase or planar phase. I think that case, I think that's in helium-3 language, that's like specifically refers to a case where you have
Synthetical. Yes.
yeah.
Well, another question is that for half quantum vortex, you described spin supercurrent circulation.
Yes.
Yes, I agree. There is also spin supercurrent circulation, but there is also a mass supercurrent.
Yes,
circulation
sure.
also.
So mass supercurrent is reduced by half,
Yes.
and spin supercurrent is something we would not have for the conventional H over 2E vortex, but it exists here. Okay, now it comes to why this suddenly became an interesting topic. Well, one thing that people have known at least since early 90s, maybe it goes longer, further than that, is that if you have P plus IP superconductor in 2 dimension and you have an axisymmetric vortex, what happens is that one of the thoroughly Dijon metricon fermionic state at the vortex core has 0 energy. But this has actually very profound implication because, we are dealing, the main thing is that we are having spin triplet pairing. So what that means is that unlike the case of spin singlet superconductor, when you try to come up with this volume of quasi-particle excitation, you find that it's a superposition of particle and hole of same spin. And when you put that together with this Bogoliov-Dugen spectrum symmetry, you find the result that if you have a 0 energy state, the mode operator for this state would be such that its Hermitian conjugate will come back to itself. In other words, it will satisfy this Majorana condition. And this is very exotic because if you have this mode with this kind of property, it means that you simply cannot define occupation number of this mode. It must be paired with another of these Majorana 0 mode if we are to talk about any kind of state occupation. But note here that I wrote down spin index. And that will tell us why having half quantum vortex is meaningful, because, if you have H over 2E vortex, that means that both spin up pair and spin down pair will each contribute one of these 0 mode. So within the vortex core, actually you can come up with 0 energy state whose occupation number you can define. You can just have easily come up with this 0 energy state annihilation operator just from the same vortex core. Which means that by applying some local perturbation at the vortex core, like some Zeeman field, you can actually destroy the zero. You can actually make the eigenenergy of this particular state non-zero. So the zero energy state can be destroyed by local perturbation in this case of h over 2e vortex. However, if you have h over 4e vortex, then you can. It means that it's a vortex that can be seen only by the up-up component and not by a down-down component. So that means that you would only have the spin-up. You would only have the Majorana zero mode coming from the spin-up component and not from the spin-down component. So if you ever want to pair this up to create a zero-energy state, you'd better get your second partner from other vortex. So once you have separated out your Majorana zero mode this way, you simply cannot destroy the zero energy state by just applying local perturbation. You have to do something non-local, like, maybe suppressing the pairing gap between these two half quantum vortices or something like that. You absolutely have to do something non-local if you want to destroy this kind of zero energy state. And also, since this is a zero energy state, whether this zero energy state is occupied or vacant is not going to change the energy. Which is to say that once we have these half quantum vortices, we are going to have a ground state degeneracy, and this is a ground state degeneracy that is protected against any kind of local perturbation. And even more amazing and exotic property of these kind of half quantum vortex configuration is that when you take one of the half quantum vortex around the other one, when you have more than 4 or more half quantum vortices, it turns out that you can just rotate from one ground state to another ground state. So this is kind of like the non-abelian statistics that's discussed by Nick Reed and other people. And this is kind of thing that really spurred on this kind of interest in half quantum vortices in P plus IP superconductor.
Like, how can it be the conjugate of itself if there's a spin index? This doesn't, like if you take the Hermitian conjugate, does it like have the opposite value sigma? Like one would have spin a half and the other would have spin minus a half? It's like the SC concept?
I think there's something about the sign that's different for spin triplet when compared to spin singlet. Yeah, I'm not sure whether I'm getting your question 100%, but I think one thing that certainly happens is that, when you compare like a spin singlet to spin triplet, yeah, this holds in spin triplet only because it's spin triplet, I think. Yeah.
You're only talking about triplet.
Yeah. So I have now finished my propaganda for half quantum vortices in P plus IP superconductor. So now is to really get down to really think about the physics of the superconductor. The main question will be, energetically, is it possible to have half quantum vortices? Well, our starting point would be this gradient free energy in London limit. And, something like this has been studied in lots of different contexts. I think Egor was we only studied this in terms of spin triplet superconductor, but like Steve and Leo really studied in some very different context where this additional phase degree of freedom really has completely different physical meaning. But I'm including all of these because of one central fact. If this was a spin singlet superconductor, we would only have this screen charge current, energy coming from screen charge current. This would have been it. These things boxed by blue would be just all there is to it. However, when we have an additional phase degree of freedom, spatial variation of this additional phase degree of freedom is going to incur extra energy cost. So, one naive argument one can fall into when one thinks about half quantum vortexes, like, okay, the overall phase winding is reduced by half, so why would its energy cost not be reduced by, say, 1/4? But that would not be true at all. That would be true as far as its energy coming from this charge vector is concerned. But the energy from charge vector is not all the energy there is. There is extra energy coming from the spin degree of freedom. And in this case, actually this is a serious problem, because whereas the charge current is screened, which means that vortex would incur only finite energy cost, the spin supercurrent part is not screened at all. Which means that if you happen to have any kind of winding in this spin phase, it's going to incur logarithmic energy cost. So not only does smaller overall phase vorticity not ensure reduced energy cost, but actually, if you have a non-zero spin phase winding in your system in the bulk, it's simply, the energy cost will be divergent. So in this sense, it actually looks very bad.
May I ask a question? So what's the justification for this form of free energy? Is it simply assumed?
No, it's not.
Have you derived this from more general principle? Especially I'm wondering whether there is a coupling between gauge delta phi and the phase alpha. You assume the phi and alpha are decoupled here. But
That is a very good question, and in general, I think there's a very good reason to, in general, I think you're correct, actually. But usually when you deal with a spin triplet superconductor, it turns out that usually the D vector actually likes to align in parallel to the direction of the angular momentum of the Cooper pairs, orbital angular momentum of the Cooper pairs. However, if you apply strong enough magnetic field along that direction, the same direction, it actually wants to be perpendicular to this fixed direction. And after that, any kind of like a coupling between the spin and orbital degree of freedom becomes very, very small, in which case this kind of free energy is justified.
Here you already mentioned some very strong condition about external field.
Yes.
So maybe I think you need to comment upon those underlying
Well,
assumptions.
what type of coupling are you thinking about?
Well, usually there is a spin and the gauge coupling,
Yeah.
especially for this intricate superconductor. But here there is no coupling between phi and alpha.
Do we mix the gradient term?
Gradient coupling? That's not.
Or yes. In
You mean
the form
grad
of
phi,
freedom.
grad phi, grad alpha?
Yes.
I think that's not allowed.
No.
That's not allowed.
There is. In a general
Spin orbit coupling.
spin orbit or
Spin orbit coupling.
spin gauge. Yes, there is in general such coupling allowed.
Yeah. I agree with you, actually. But, let me say this. at least one thing we can say is that this is the most favorable scenario for half quantum vortex.
If you assume, think of that as two components, one of is up and one is down.
Yes.
If they have a slightly different superfluid density, then you would have this case.
Yeah, that's
You can
also
just
true.
write it out very easy.
Right, because these are rotations of.
Yeah, so this one basically assumes that the superfluid density for the up and down still
same.
remains the same even if you
Yeah.
have a wide field.
It's because this theory came from some grad phi up and grad phi down,
Yeah,
and then you rotated it.
you write back in terms of the up and down,
Right,
and then you
and then you
rewrite that,
rotate
then
into
you would
this.
see whether you would have.
And you can rotate into this if the two coefficients are the same. in the
That's right.
original.
That is exactly.
To rephrase this, so my justification is this. So this is the theory that would give us, that would be most, in absence of spin polarization of the condensate, this is the theory that will be energetically most favorable to half quantum vortex. So it would be worth examining how half quantum vortex would fare energetically within the framework of this theory. That's what I would say. And when actually there are like a lot of justification for using this on real system, but that actually would involve lots of machinery and lots of additional physics. That you're absolutely right about that. But I mean, the case I mentioned in the previous slide may have been rather actually quite unfair for the half quantum vortex, because basically one half quantum vortex and one conventional vortex, that's simply not topologically equivalent. So maybe we should really think about a pair of half quantum vortices that would be topologically equivalent to one conventional vortex. And this kind of pair would give us that case, because both of them have pi overall phase binding, and one has plus pi and the other has minus pi binding in the spin phase. So when you just kind of like combine them, when you see them from like very far away, they would really look like a one conventional vortex. And in this case, at least you can speak of energy competition. So as far as the charge sector is concerned, there will be magnetic repulsion. But still, the spin current sector would actually have caused attraction between these two half quantum vortices. And the bad news is that whereas the repulsion in charge sector is screened, the attraction in the spin sector is unscreened. So the best we can hope for is actually gives us some kind of a bound pair. Or even worse, like, we're getting some kind of bound pair only because we're assuming that the spin phase stiffness is smaller than the charge phase stiffness. But, so at this point, this whole half quantum vortex energetics looks pretty bad. But we still have something to take away from here. Because, I mean, it has been argued by Tony Leggett in the past that, for this spin phase stiffness should be smaller than the charge phase stiffness, overall phase stiffness. And you can see that if you have very small rho SP over rho S ratio, this pair size can be, the equilibrium pair size can become larger and larger. So that actually gives us some hint about where we should look for at least some moral equivalent of a half quantum vortex.
So the existence of that minimum means what? That it's favorable for half vortex? Or I'm trying to...
Yes. So this is like when the pair shrinks to zero, it means that you're going back to full quantum vortex.
Oh, I see. So you think of it as two halves that are
Yeah.
tied together
Yes.
by some linear energy or logarithmic?
It's logarithmic energy. So at short distance, both of them are logarithmic, but at long distance, I mean, screening cuts off the magnetic part, whereas the spin current part is unscreened.
parent at the up. That's condition. So because of the charge part is electromagnetically mediated
Yes.
logarithmic interaction becomes power law at a short distance. So it becomes weaker.
No, it's like some.
They cancel each
Yeah,
other.
some modified Bessel function kind of thing, K0.
Yeah.
I'm trying to understand why isn't half always, why isn't favor over the full? That's what's confusing.
Oh, because the energy cost coming from the spin current circulation.
Oh, I see. While the full one, you're going to put a full one in the screenable, in phi, right? When you say full, you mean full, not an alpha, but full in phi.
Yes.
The one that can be screened.
Yeah. So actually, the full would not really have any kind of spin supercurrent circulation.
Yeah, but I mean, these arguments, you're thinking about 2D?
Yes, this is really more 2D argument, or at least you're just ignoring any kind of like a vortex line bending.
Right, but then you have to use screening length.
Yes, well,
That's, it's an effective screening length that's diverges in the limit of vanishing film thickness. It goes as lambda squared over d.
Yes, I understand.
And so,
Yeah, it will favor bigger and bigger splitting. As the longer is lambda,
Yeah.
the longer is big. So it actually it's
well, exactly, but that length can be astronomical if you're really thinking about it.
That's
If you
true.
really think about it, real films.
That's true.
So this difference can be quite tiny.
Yeah. So, but one thing is that I want to, from the cold atom viewpoint, I once talked with one of my friends who is a cold atom experimenter with him. When I brought up the subject of half quantum vortex, he was like, with spinor condensate, that's a piece of cake. Why do you even think that's a problem worth studying? But the main message there is that, in spinor condensate, mass current and spin current are both on screen. But here, even if the screen length is large, it is a really fundamental difference really between the charge current and the spin current. And that really makes it, it does make it qualitatively worse for the half quantum vortex.
Could you repeat that again? Could you repeat the difference again?
So in cold atom, both mass current and both mass supercurrent and the spin supercurrent is on screen basically.
Because it's neutral.
Yes. So because of that, half quantum vortex is really that's really no different from full quantum vortex energetically in some sense. However, in the superconductor, the situation is qualitatively worse for half quantum vortex because usually when you split full quantum vortex into a pair of half quantum vortices, it saves energy in the mass current sector, but it incurs energy cost in the spin supercurrent sector. But spin supercurrent is unscreened, whereas the charge supercurrent is screened. So it makes things it makes the energetics much more unfavorable to half quantum vortex when you compare the situation of superconductor with the neutral superfluid.
When you rotate a spinor condensate, doesn't the rotation only couple to charge like this, or what's?
That's certainly true, but still, when it comes to screening, I think the way to answer your question is, sure, you will have something like this, but you don't have this term.
Okay, so here you minimize A, but rotation you don't.
It's
It's
just
just completely decoupled.
Let's see, I would say picture is more favorable than you paid for half a vortex because of this that in 2D screening is very weak. Okay, it's not actually not even exponential. And so as a result, you have this pro solution for the 2D screening problem. So as a result, if this screening effect didn't come in, then you definitely favor two 1/2 vortices over one full vortex.
Well, I guess that
And so,
usually the system we would study is like more like the layered P plus IP superconductor, which strong conductance is believed to be. So in that case, I guess it's not like lambda becomes really that large.
yeah, so in that case it's not.
Yeah.
But if you're really looking at 2D case, I think it's much more favorable.
But I mean, we are already getting some hint how to approach this problem because, you know, these parasites can become like a comparable. They should be taken as comparable to the screen length. So maybe the way to go is to go to microscopic sample with dimension close to lambda. I mean, this is the idea that Hendrik actually gave us. I mean, he co-authored with Una and me on theory paper, but he's actually an experimentalist. But anyway, he came up with this idea, and you know, it really made lots of sense. I mean, because it simultaneously takes care of the problem of the log energy divergence for spin supercurrent, while the effect of the screening also becomes much less significant. So in this megascopic setting of this megascopic sample, it's not quite, we are not quite talking about vortex. It's more of like a problem of fluxoid entry into the sample. So the whole issue here is that what overall phase winding and what spin phase winding should you have around the sample at given magnetic field, given applied magnetic field. That's in such a way as to minimize this Gibbs free energy. But what we found here is that if this stiffness ratio is really small enough, we can have a case where this we can actually have a local minima where spin phase winding number is non-zero. Because usually in this case where we don't have this spin phase winding part, we have this constraint that the overall phase winding should be integer. That's really required to have the single valued condensate wave function. However, in this case, all we require is that the sum and the difference between this overall phase winding and the spin phase winding should be integer. So we can actually have solution like 1/2, 1/2. And if the stiffness ratio is small enough, we actually find that that kind of solution can be a local minima. So,
are more general solutions allowed, or I mean, at least topologically, are you allowed to have any other fraction that adds up to 1, or it has to be 1?
No, it has to be 1. I mean, the condition is that the sum and the difference should be integer.
Okay.
So, but this Gibbs free energy still looks very abstract. It still leaves the question what kind of experimental signatures that is going to lead to. But then there's a piece of thermodynamics that we all know. Namely that if you differentiate this Gibbs free energy by applied magnetic fields, you're going to get the magnetization of your magnetoscopic sample. So if you don't have this small local minima, you would just have gotten some regular sawtooth pattern for the magnetization curve. However, if you have this small local minima that corresponds to half integer fluxoid, you are actually going to have a double sawtooth pattern for your magnetization. And magnetization is certainly something that can be measured in experiment. And in fact, this double sawtooth pattern was observed recently in experiment at Urbana. You can see that as you ramp up this.
Can you talk about the sample a little bit? It's a mesoscopic sample?
Yes. This is the kind of length scale we have. So it has a hole, but the shape is quite irregular. And basically, this cantilever has its natural frequency, but when you place it in a magnetic field with some magnetized sample, the natural frequency is going to shift because of this additional torque. And by measuring this change in the vibration frequency, they can actually measure the magnetization of the sample.
This is a magnetization corresponding to this half vortex that's
oh yeah,
that's
let me see. So if you just have this kind of sawtooth pattern, then all you have seen is the integer fluxoid entry. But when you start to have this kind of smaller sawtooth in your magnetization curve, that's indicating that you have some kind of a half integer fluxoid entry.
So these curves are really a detection of the steps in the natural frequency of this oscillator?
Yes.
As you crank up the field, I see.
Well, if this is a really real confirmation, then it must be a real breakthrough because it confirms, it finally vindicates the P-wave nature of strontium loosening. That's why I'd like to ask a few questions. Well, actually, is there any possibility that those kinks are due to the transverse magnetization penetrating through the edge of the sample?
Well, there are two arguments against that.
Yeah.
First is, as you can see, this sample size is very irregular. Sample shape is quite irregular. So in your scenario, what one would expect is that if we rotate the direction of the in-plane magnetic field, we should see some change in the magnetization curve. And they have not seen such a thing. And the other is that...
So they have checked that?
Yeah, they checked that, and another thing they checked is that they looked at the how the magnetization will change when they only apply the in-plane magnetic field. And they did not see any kind of kink until like a, let me see. Yeah, they have not seen any change until like, I think 200 Gauss, but they started to see this kind of double sawtooth pattern from the in-plane field of like 40 Gauss. So presumably what they are seeing under 200 Gauss may not, I mean, there's no reason to, they don't see any evidence to conclude that it's really coming from the in-plane magnetic field.
Sorry, I missed that. So what are those numbers on the right?
Oh, this number, it's actually a bit confusing. The Hx is the magnetic field you apply along this axial direction, and Hz is the magnetic field you actually apply in in-plane direction. So this is actually a rather surprising and puzzling part that, only when you apply some small but non-zero in-plane magnetic field, you start to see half interior fluxoid entry.
So those numbers are Hz on the right hand side, or is that?
This is the axial magnetic field, and this is the in-plane magnetic field.
Why is it called Ux?
Yeah, it's just to indicate. Let me see.
No, but I thought that's magnetization. I mean, it looks like the magnetization curves. I think the numbers.
Oh, let me see. Oh, yeah, this is magnetization.
That's magnetization, but different curves are labeled.
Yeah, I'm sorry. This is magnetization. This is the value for magnetization, and this is actually value for different curve has like a different in-plane magnetic field.
And those numbers in what units?
Yeah, millitesla. It's this, the one on the right and the one on the bottom are in millitesla. I mean, like,
It's very large.
I mean, it's
I
like
just mean in-plane one, if the in-plane field is measured in the same units as the axial one.
yeah,
quite
in-plane
large.
is in-plane is large. That's true compared with the axial direction field in axial direction. On the other hand, they did not see any kind of like a vortex entry in-plane direction due to in-plane direction for like up to this value. To without, yeah.
I still didn't get that. So what is the role of the in-plane field? What is it supposed to do?
What we suspect is that, if we have a slight spin polarization of the condensate in this in-plane direction, that would actually make it easier for you to have this kind of half quantum vortex. Because mainly because, in that case, I mean, having half quantum vortex just implies that you have less.
Doesn't it?
Yeah. So if you have if you have circulation only for the component that has larger Zeeman energy, that kind of saves your energy in some sense. In a sense.
Your D vector is in plane, right? So when you apply an in-plane field, it's
No, I don't think we have really reason to conclude that. In fact, I think the fact that there was no dependence on the direction of your in-plane field suggests that, at least in equilibrium, D vector is really out of plane. If D vector was fixed in some in-plane direction, applying each kind of in-plane field would really pin the D vector, but we have seen they do not see any kind of such effect.
Remind me, for this compound, do you see a different light shifts for magnetic field in different directions? I thought you didn't.
No, you're exactly right. That's exactly correct assessment of the current experimental situation. So in that sense, there is no direct evidence about which direction your D vector is pointing at.
So then what's the point of the horizontal field?
I mean, it's one of the big mysteries of the strong translucent 214. I really agree with you on that. But I mean, if you're interested in this experiment, I'm more than happy to send you the manuscript.
Okay.
This is not published.
No, it's not published yet.
What are the dimensions of the sample in terms of coherence length and penetration depth? At whole.
Let's see. Penetration depth was like 0.1 micron. Let me see. I think it was roughly comparable to the coherence length, penetration depth.
And coherence length is a factor, so the one sort of for this material, one sort of the bulk penetration slide. So the whole, so then the whole sample is comparable to coherence length.
I think it's more comparable to penetration depth, but penetration depth is only like 2.5 times the coherence length anyway, so
2.5 to 3.5.
something like 2.5.
Can I ask a simple question? If I think of the D vector now, and when you add in an extra half vortex. So what is happening to? You said the d vector. I thought that made the d vector rotate now.
Yes.
But you said it was along the.
So it is possible that the
mean,
d vector is actually rotating out of plane.
it has to, doesn't it?
That's
But
what that's.
I thought it was going, as you said, I thought it was going to rotate like that.
Oh,
So you
and
can't
this is the problem. I think the main reason why people thought that d vector should be rotating in plane and not out of plane is that, you know, if you want to rotate out of plane, you have to break loose from the main spin-orbit coupling effect, which would really pin this d vector to crystalline z-axis direction.
But I mean, if it rotates like that, it has to rotate around some axis, so that
Yeah.
you pick an axis in the x, you know.
So we are believing that it's rotating around the direction of the applied in-plane magnetic field. But that certainly would involve rotating around, somehow breaking away from the z-axis direction, where many people, it has long been thought that there should be some pinning of the d vector. But it may be that the pinning of the d vector in this z-axis, crystalline z-axis direction is so weak that, you know, it really doesn't matter too much.
But would that be the explanation why you need an in-plane field, and that would provide you an axis, the preferred axis? To
Yes,
rotate
that's
around?
what we are thinking.
Okay.
That's what we are thinking. But I mean, I have to say that this is interesting because we are seeing the signature of the half-integer fluxoid entry, but lots of the physics coming from the Strontian-Muslin 214 are still, you know, not really understood at this point.
Is it known how d vector is supposed to couple to external field?
Oh, d vector is supposed to prefer to be perpendicular to the external field.
Yeah.
That's clear.
That's generic. That's a generic statement, or that's
That's general
That's a generic-
for any spin triple
The
superconductor.
Zeeman field aligns the spins.
Oh, I
That
see.
does it.
Or I mean, I mean, this, if you have a spin triplet superfluid and you apply magnetic Zeeman field, you know, the superfluid would prefer to have that direction as the equal pairing direction. Since in that case you can actually respond to the Zeeman field without breaking up the pairs. But the equal spin pairing direction is always perpendicular to the d vector direction. So since the Byron zero mode is supposed to be the, you know, glamour of this half quantum vortex, let's think. I'll just comment on what the implication for the implication this half quantum fluxoid entry would have here. So basically, since we don't have any vortex core, you know, this spectroscopic sample actually is a whole fluid. What we would really have is not a vortex core state, but edge state around the inner and outer edge. And if you insert this H over 4E flux, actually a total number of Majorana zero mode should be even in the sample, but it's just that both around the inner and outer edge, you will just get one Majorana zero mode each. So this would be like a table of how this zero mode, what kind of zero mode you'd have for each flux.
Is there any theorem that would guarantee that you have such a zero mode in this geometry?
Yes, it's kind of like changing the. It's really analogous to changing the boundary condition for this chiral Majorana field psi in the case of this 5-half state of torus. It behaves in very similar fashion.
No, but I mean, given, is it an index theorem that holds for some Hamiltonian that describes this thing? Or, I mean, what's the status of it? Because even for the ordinary Majorana zero modes, it's as you know, there are certain claims about index theorems there, but I think...
Oh, but actually, I think this is the best way to answer your question. Why this? I mean, we can actually regard this as being topologically identical to vortex zero's vortex core state. Just consider it this way: you have a sphere, and you place vortex around the both north and south pole. Really, this geometry is pretty much same as that. That's the way you think about it.
Yeah, no, I think I can think about it in many ways.
That, I'm not really sure about the really mathematical formulation of this the kind of index theorem. I know that Victor and you worked on it, but I'm just a little bit confused about.
I mean, ultimately, it's a Dirac equation with a mass term that's locally changing sign at the boundary, so you're guaranteed a mode there, just because of the mass term changing sign. That's really what the Majorana mode is.
Yeah, but I mean, this is a real boundary. It's not.
Yeah. Yeah, it's changing sign across the boundary. If you would.
Okay, we can discuss that.
Okay, so we have discussed the one case where this half quantum vortex can be stabilized and detected. That is the mesoscope example, and I will also mention the second part, second possibility, which happens in vortex lattice. So I need to first talk about how half quantum vortex would look like. And basically, the picture is that we will have some superposition of the vortex, up vortex lattice and down vortex lattice. And these two vortex lattices would would have the same vortex density. That will be like the, zeroth level description of the half quantum vortex lattice. And this is, in some sense, quite analogous to this anti-vortex lattice that was proposed for helium-4 superfluid by Aaron Capitulini and Shuchen Zhang in the early 90s. There, the main message was that you have this kind of superposition of anti-vortex lattice and the vortex lattice, and the overall vorticity of the system was 0. So if you translate this to the this half quantum vortex language, here what we would have is that as far as the overall vorticity is concerned, it should certainly be non-zero. In fact, the up vortex and down vortex would have same pi winding as far as the overall phase is concerned. However, their spin phase winding should cancel out. So this is like the basic picture of the half quantum vortex lattice. And the reason why this may be another good place to look for half quantum vortex is that, in some sense, you're really reducing the system size down to the vortex lattice constant. So in that sense, we can actually expect this to be effectively mesoscopic. So let's look at how we should take care of the energetics here. So the basic tactic here is, the basic tactic pursued by when I worked on this problem with Dan Eckerberg and Una is just take this Gibbs free energy in the Gibbs-Landau theory, and we treated the problem with a case when we're close to the upper critical field. And there, what we can do is that we can use the linearized Ginsburg-Landau equation, and on solving that, we would find periodically vanishing lowest Landau level wave function. And what we do with that is that we put it back into this original Ginsburg-Landau free energy, and we investigate the energy expectation value we get out of this. So in that case, what would happen is that we would get some, depending on whether we have full quantum, full vortex lattice or half quantum vortex lattice, we would get different value coming out from these quartic terms.
So you reference these earlier works. How
Yes.
is yours different from what they did? Did they do the problem you're trying to do? Or?
They actually, what I learned from this paper is actually how you figure out the triangular vortex lattice to be lower end with the sphere vortex lattice. And I think they also pursue some FFLO state.
But did they do it for this triplet? Did they do it for this triplet too?
No, I think they didn't. The quartic terms were different because they weren't treating the triplet superquantum. Yeah. It was some kind of FFLO, but I really haven't really managed to figure out what's the exact problem they were studying. But I mean, the term we should take a look. We should really take a look. I mean, the one on this upper line. It's just like taking two copies of the Ginsburg-Landau theory you're all familiar with. It's really these two beta prime and gamma terms that really look different. And one thing we need to notice here is that this term actually tells us how we can get the difference between two-phase stiffness within this framework of Ginsburg-Landau theory. If this gamma is larger than 0, then we can have the spin phase stiffness smaller than the overall phase stiffness. So that would favor half quantum vortex. On the other hand, one term that we never worried about for the London limit, but we need to worry now is the vortex core interaction. So if this beta prime is negative, then we have core attraction between two different types of half quantum vortices. That would really compete with this positive gamma term. So this kind of energetics will certainly also not only affect influence the result of whether we are going to have full vortex lattice or half quantum vortex lattice, but it will certainly have impact on what kind of structure this half quantum vortex lattice would take. So we not only need to think about the interaction between the half quantum vortex of same species, but we also need to think about what we can call interlattice interaction, like the interaction between half quantum vortex of different type. And curious thing is that regardless of the details of the theory you put in, generally what happens is that when different type of vortices tend to attract, you of course stay in full quantum vortex lattice, but if they start to have some repulsion, when the repulsion is not too big, you're going to get, and you start from the triangular lattice, you tend to get honeycomb lattice, but when the repulsion gets stronger, you usually end up getting interlaced sphere lattice, and when this repulsion becomes stronger, you have some kind of like a elongated rectangular vortex lattice structure. And all these papers, I mean, Jason Ho certainly used some free energy that's different from what Ryan used, and that is again a little bit different from what Dan Eckerberg and I used, but the result came out qualitatively similar, so that's one interesting fact. But, so one might wonder, just by looking at this vortex lattice structure, it looks like, full quantum vortex lattice has very different structure from half quantum vortex lattice. However, this may not be really true because, the energy difference between different lattice structure in full quantum vortex lattice is not all that large, and when you put in something like a crystalline anisotropy and so on, it is actually pretty easy for the full quantum vortex lattice to have a square structure. And one might ask the question, how are you going to distinguish the interlaced square structure of half quantum vortex lattice to just the square lattice of conventional vortex lattice? In that case, one thing you can do is neutron scattering. Because of this Zeeman field coupling, there is going to be some imbalance between up-up pairs and down-down pairs. And when you do this kind of neutron scattering, this half quantum vortex lattice will show modulation in the peak signal strength, but they would not be present in the case of full quantum vortex. Okay, so
sorry. Why not that you just have some structure factors in the neutron scattering pattern?
excuse me?
I think that's what you're doing.
Yeah, that's what I'm doing actually.
But you said that you need a spin imbalance. Should not be done.
Well, I think the question may be like, is there any way that what you see in half quantum vortex lattice is qualitatively different from what you see in full vortex lattice? And this kind of peak modulation is not what one would expect from full.
Yeah, if you look at some of the pictures that you have in the last view graph, the last one, backup one. There's some of the, I mean, if you split the half vortices into two, the lattice size is already different from the ordinary full vortex lattice size, right?
That's true, but that's only quantitative. So we're just wondering if there can be something qualitative.
Okay.
And lastly, I'm going to just briefly mention what I'm working on right now. This is what we are thinking about is entropy-driven formation of half quantum vortex lattice. And we all know that, basically the phase a system is going to settle in is the phase that gives us the lowest free energy. So at finite temperature, if you can get into some phase that has higher entropy, that phase would be favored even if it has larger. It may be favored. It may be stabilized even if that phase has higher energy at zero temperature. And what we are finding is that because half quantum vortex lattice, when you think about the collective excitation, we have larger entropy. And because of that, we are going to have this kind of phase diagram where close to this transition between zero temperature transition between half quantum vortex lattice and full quantum vortex lattice, this phase boundary is actually slant toward the full vortex lattice side. Kappa would be like the rho, of course, it would be the analog of the rho SP, and rho would be analog to rho S. Well, when you talk about when you just say entropy, you can also consider the case where this stiffness ratio is normalized due to entropy effect, and this is something that Ryan studied with Suboto and Joel. But what we are saying is that if you think about the collective excitation of your vortex lattice, even without any kind of renormalization of the stiffness ratio, you can still have this kind of entropy-driven transition.
So what's the argument is somehow though, it's the entropy of the phonons?
Yes.
Somehow you have more.
Yes, exactly.
But, okay, so this is very similar to this Capitoni work you mentioned.
Yes.
That was the argument for this vortex and divertex. Which I remember at the March meeting after Captain Week's talk, Michael Fisher got up and said, this may be in principle possible, but I find it very unlikely.
Well,
And
I
the question
think,
is, can you estimate, is there any regime in which you can argue that the entropy is enough to beat the...
But it's a different problem.
But it's a different
Vortices
problem
and
because-
vortices can recombine.
yeah.
You see, in this case, he's just counting phonon degrees of freedom. And so even though the energy is lower in the ground state, as you go up, there's a factor of roughly 2. That's
No, but
the
they have to-
entropy.
So log 2 has to beat some large log for him. It's still, energetically, they're different by a log of
But
some.
it will for sure eventually, because the thing will melt. So what he's saying
Well, the
is
question
that-
is, will it beat it before the whole thing just melts? Right?
yeah, so
That is
that's the
the
right
question
question.
we are really avoiding for our problem.
Right. If the thing is stable up to, temperatures.
But I think that's okay here because one argument we're going to present, I mean, it's not some, I will not go into detail here, but like,
I just want to understand the
this
argument.
would make sense only if we stay way below the temperature scale set by like Brzezinski, Kostolos-Talos kind of scaling. But I mean, the temperature we're going to discuss here will be like something like that, between that and the the n over rho, where rho is the electron density and n is the vortex density. Below that, there's going to be lots of quantum effect, which we're just ducking right for this paper. So, I mean, this entropy, this collective excitation entropy can be just understood in this way. I mean, we all know, something that we can just immediately see as the single particle picture. If you split this one full quantum vortex into a pair of half quantum vortices, you're certainly going to gain this configuration entropy. And this kind of effect actually persists down to the many-body picture because, when you compare these half quantum vortex ladders to the full quantum vortex ladders, one thing that you can immediately see is that whereas this full quantum vortex ladders is not going to have optical phonons, these half quantum vortex ladder is going to have, it is sure to have these optical phonons. And the fact that these additional optical phonon modes come into existence will be what drives the transition from the full quantum vortex ladders to half quantum vortex ladders. So I think I ran a little bit over time, but thank you very much for your attention. And these are my conclusions.
Could you take care of the next talk if you're around? Huh?
Three. Oh, next.